Hello everyone, welcome to this video. In this video, we'll be talking about CUDA, image processing in CUDA. So basically, we'll be using GPU for processing images, and in this one, we will be basically performing four processes, which are the first one will be the blur, the second one will be the edge detection. The third one will be plotting a sine wave, and the fourth one will be uh, a, uh, it will be a custom function. It's known as let me see where it is. Uh, yeah, it's Vignette effect, which is basically you darken your picture on the edges. So before proceeding further, I will just go through some basics about CUDA. So let's just go through CUDA. And I would like to mention that this project was undertaken as a part of the course offered at University of Tennessee. The course is parallel algorithms, and it's taught by Dr. Yang. So first of all, CUDA is a language developed by NVIDIA for GPUs. So it helps to do stuff on GPU. So putting in context, so it's more or less similar to C++, just there are few more functions or uh, terminologies that helps you run things on GPU. So let's just go through basic stuff. So few things that you need to know for GPU offloading. That is once when you uh, perform something on GPU. So the CPU one is known as host and GPU is known as device. And CPU and its memory, it's part of the host memory, and GPU has its own dedicated memory. And why do we need GPUs? Is that because GPUs has thousands of concurrent threads which can do graphical, like graphics as thousand and million of pixels. So those kind of things can be done pretty fast on GPUs compared to CPU. So so our code structure will be something like this. So there will be some serial part, some parallel part, which will be done on the GPU. And yeah, so on like when you are running on a serial, you are running on one thread, and then you are creating multiple threads, and then again you have some serial part will be running on a single thread. So this is how it works. Like you have some variables on CPU, you will create a copy for GPU. You will be copying that, and then GPU will be performing operations, and then you will be copying data back to the CPU. So a simple example is this one. Like you're printing a hello world, and the compiler in this that we are using is NVIDIA compiler, that is NVCC, and you will be requiring CUDA module for that. I will talk about this later. Okay, so to define a function that runs on GPU, you need to define it like this: global underscore void. So if you define a function like this, then the compiler knows that this one should be run on GPU. And there is something called kernel launch. So this is a way to launch a GPU kernel in which uh, these two numbers define the number of groups and number of threads, which we'll be talking later in more details. Let me just skip these things. Let's see. Yes. Yeah, so this is what I was referring to. This is a kernel launch, and this can be any arbitrary function that is defined in the manner that we talked before. Yeah, so the first one refers to the number of blocks, and one block has multiple threads, and the second variable is the number of threads. So let's just discuss about that. Okay, so we have one example in which we are doing a sum operation on GPU. So here these refers to the pointer to the memory in which the values for A and B and C are stored. So this is how you define a function for GPU. And similar to your C, where you have memory allocation, free memory, and memory copies, you have similarly on CUDA. For CUDA, for GPU, CUDA memory allocation that allocates memory for the GPU, then CUDA free, which free up the CUDA GPU memory, and then you have memory copy for copying from host to device and vice versa. So let's see. Okay. Yeah, so you can understand the concept of thread, block, and grid like this. So like we are running on GPU, on CPU. So CPU has multiple threads. So so this represents the one thread. And when it comes to the block, it's a collection of a number of threads. And then a grid has a number of blocks. So this is how it works. So you have a grid, and in that you have multiple blocks, and each block has multiple threads. And these threads can be identified based on their IDs. So so assume that you have this one. Let's see if I can use a point. Yeah. So this is a grid in which you have multiple blocks, and each block has multiple threads. So, so if you want to identify this particular position, you can access the block ID that is 0, comma 1. That is 1. So the block ID is 1. Then you have thread index. So what is the thread ID in this? Block ID is 1, and the block dimension is 4. You have 4 threads in X direction and 4 in Y direction. And similarly, X index and Y index is over here, and the relative position of your thread. So it's 0, 1, 2, 3. So it's 3 over here and 1 in the Y direction. So this gives you it. You can consider it as a grid. So in this, the seventh and ninth, a cell which is at seventh and ninth X and Y will refer to your uh, to the thread that will be operating on your function. Okay, so let's move to our code. I think it's over here, yes. So we are doing image processing. So let's go on top. Yeah. So these are some of the uh, libraries that you will be needing. And yeah, so yes. So initially we are doing a memory check on GPU if during the memory allocation process, if it runs into an error. So by using this function, we are printing it explicitly so that we know that something went wrong with the code. So in this one, we are giving an image file as an input, and we are using ppm format. So if some of you don't know about ppm format, it's like this. So it's a simple RGB binary format. So you can't read it. It's only for the computer. And on the header file, you have a P6, which indicates that it's a ppm format P6. And then there is a comment line, and after that, it provides the width and height of your image. And in the next line, you have the maximum, that is the maximum RGB value. And after that, you have in a triplet fashion, you have your RGBs, red, green, and blue data. So it is when you provide an input file, it is being read in this. Uh, so it converts into a .c star file, which can be read by the compiler, and then if it cannot open, it will print an error. Then it looks for in the first line. This indicator skips all the white spaces, and it directly goes for the first few characters. which are without the white spaces. So it locates P6 on the first line, and if it doesn't recognize this P6, it will throw out error. And then again, it skips the white spaces, and then in the next line, it will look for the comment. Okay, so it will look for the comment and then it will move forward. And in the next line, it will look for the width and height, and the next one will be the maximum color. So in most of the cases, it will be 255. Not in most of the cases, it depends on the picture, but the maximum value will be 255. So then we create a array for storing the RGBs. So basically, it reads everything in read. It reads all the data, and then this data is divided into R, G, and B correspondingly. So here we are using 3. I will refers to the I0. Yeah, so like you have 4 by 8. If mm, yeah, let's do it over here. So if you have 4 cross 6, if this is the width and this is the height, so you have about 24 uh, RGB combination in your file. So that's what it looks for. So in each one, this I goes for 1, it's 0, then it becomes 1, then 2. So this goes like this. So after reading the data, we are resetting the arrays. So then this is the code. This is the function for writing the data in ppm format. It's similar thing. We'll be integrating P6 and then we'll be writing out the uh, RGB for the image. So let's go to the function. So as discussed before, global underscore wide will tell the compiler that it should be run on GPU, and now we have a function called blur, which inputs the width and height, and weight, which will define like how blur you want the image to be. This is one of the parameters that you can play with. And then you have these R in and G in and B in, and then it outputs these 3 RGBs. This here will refer to the current thread that you will be working on. So to understand this, let me show you over here. So there is something called block index, which if you want to parallelize your code with multiple blocks, like the one which is done over here, so you can use the block ID. If you can see over here, I think somewhere it should show up. Maybe not here. Okay, so similar to that, you have thread ID, and when you have multiple blocks and multiple blocks, and each block has multiple threads, this is the way you can define the index to individual threads. It basically goes to your block, the block ID in X, then the block dimension, that is how many threads it has in X direction, and then the individual thread ID, and similarly in Y. So the Gaussian blur is only done inside the image, so it returns if it exceeds those values. And then IDX, it basically refers to the individual pixel in the image. So W is the width, and Y here will be, it will vary from 0 to the number of blocks. So again, we define the weight. So the weight that is defined, that is used for the current pixel, and the rate and adjacent to that particular pixel, uh, 1 minus weight will be used divided by 4, and x minus 1, x plus 1, x minus 1, x plus y plus 1. This will refer to the adjacent pixels. So if you have over here, yeah, we can use this one. Let me get, yeah. So if you are working on this pixel, there will be one on top, one on left, unless you are on the boundary. For that also we have worked. So the weight W will be applied over here. And on these four, weight 1 minus W over 4 will be applied. So correspondingly, these values are calculated over here, and these are basically inputted into a CPU function, which perform other operations. So let me just show you that one. Yeah, it basically inputs the file, which is defined into input.ppm, and then from there it extracts the width and size of the file, and then it allocates memory on your on the GPU, and this is the pointer that it assigns to, and uh, n refers to the size, which will be same as your the number of pixels, which is width into height, and each pixel uses the float data. So similarly, then you're copying your RGB data to the device. So in the second input will be your uh, CPU CPU variables, and the first will be your GPU variables. And here you're defining uh, the number of threads and the number of blocks, the number of threads, which is basically your each block has 16 cross 16, and then based on that you uh, assign the number of blocks and number of threads. And this is the weight factor. So if you perform one blur iteration, you will not be able to see much difference. So I played with this number. Initially, I was using a 0.3 value, and by using that value, I was not able to differentiate between the original and the blur image. So I reduced the weight factor, and then this is the number of iterations it goes through. So this is the GPU kernel is launched 40 times over here, and after each time the data is swapped with the new one, and new one goes in, and then you're copying the data back to your CPU variables, and then this is the writing part of the image back, and then you're freeing up that memory on your GPU. So there is all the other also have similar architecture, and this is the main function in which, because there are four operations, so we I provided a user-based input for selecting which operation you want to do. It's blur, edge, sign, or custom. Let's go to the other operations as well. So in the edge detection, we'll be basically calculating the gradient. I think this can be easily explained from here. So the gradient will be defined using central difference. So you'll be calculating the gradient of your RGB values, and then the total gradient will be this. And then you will be specifying a threshold value. And if the gradient is more than that value, it like over here, if your magnitude is greater than that, then you will be assigning a weight factor of 1. Otherwise, the weight factor will be 0. So what happens here? It will give you if I don't know whether you guys know about Schillerian or shadowgraphy. So it basically gives you the gradient, the lines with highest gradient defined in the flow. So let me show you one of the examples. So I work with one of a cat and one of a dog. So if you see over here in the edge detection, it will give you uh, features which has highest gradients. So in this image, if you can see over here, high gradients will come because here it's blurred and you have a sharp edges over here. So these results into sharp gradient, and similarly over here also you will see. And the third one is sine wave. So we are basically removing all the RGB data, and at the center of your image, we're constructing a sine wave with user-defined amplitude and uh, period. So this can be seen over here. Mm, you can see, yes, amplitude is defined, and yes, it takes half of the height. It starts from there. So the last one is a custom. So we have a choice, like what particular operation we want to do. So I went with Vignette effect, which is basically uh, you will darken the image on the edges. So it basically works like you define the center and you take a radius, and as your radius increases, you increase the amount of darkness you want. So this is the function that it uses. So it depends on your radius and how the radius is defined. It is defined as dx, which is defined from the center of your image and the current cell that you're working on. And then the vector is defined as 1 minus d. So as your d uh, increases, so here d will be a non-dimensional number. So it will be, the maximum value will be 1. So at the center you have uh, a factor of 0, and as you go on the edges, your uh, so basically it goes to 0. I think I said the opposite of that. Yeah, so factor means how much you want of the original color you want to keep. So if it's 0, it will be all black, and if it's 1, you will have the original RGB values. Yeah, this is how it works. Yes. So these were the four operations that we performed on the images, and then yeah, so kernel launch and other things. Yeah, let's go to the compilation. So basically, to convert a PNG to PPM format, I used ChatGPT and I obtained this Python script which converts an input PNG file to output PPM file. And this is the way you define it. And then you can compile the code that I showed, and this will be provided as a attachment to this video. So I'll put this on GitHub, and I'll share the directory in the with this video. Okay, let's see the code, the operation of the code. So basically, first of all, you will need a GPU. So right now I'm already on a GPU, which is available with the Sim Center at University of Tennessee. So it works with for me. So let's see what all we have over here. So right now I already performed these operations, so I have a bunch of files. So I'll just remove these files from here. Here. Let's remove blur also. Yeah. So I'll show you the original file first. So this is the original image that we have here, and we'll be performing a bunch of operation on this. So to convert first, we'll use Python. It's convert and give the image name. So now we have a ppm file. So if we want to view this, I'll just show you how it looks. Much of it will be encrypted, so we won't be able to see much. So you can see over here we have a speed file definition, then you have a number of width and height, and then you have maximum color range. Here you can see we don't have any comment file, so that part of the code will be skipped. So we have this. Am I still recording? Yes. Okay. So now yes. So I have the ppm file. Yeah, I'll just copy this. Rather move it. Because our code expects input.ppm file. So I'll just rename it to that. Yeah, here we go. And now we'll be compiling the code. So to compile, we are using NVCC. And first of all, I'll show you the module. So module I'm using is CUDA for compiling this. And Anaconda for the Python script. So let's just do NVCC. I will be using optimizer O2. Then the file name, that is ppm CUDA-new.cu, and I will be compiling it to ppm CUDA-new. Yeah. So maybe it takes, it's already compiled. So we have this file over here. So now to run this, if you do this, so it will say that you need to use it like this, provide one of these options. So what it outputs is a ppm file after performing the operation. Well, let's just do for blur. If you see, we have a blur.ppm file, and if I convert it into PNG, so for that the script is Python 3 blur. The function name is ppm to PNG, and then blur. Yes, it gives you a blur file. So if we look at that, you can see that the blur has been performed, and it's very quick. I didn't check it on CPU, but I believe it will be pretty quick compared to the CPU version. So let's go, I'll show you the custom one. Custom, yes. And then let's convert to PNG. Here we have, you can see the Vignette effect has been performed. So I'll show you the edge detection also. So in similar way, you can do it for multiple things. You can play with the parameters that are defined, and you'll be able to see such. Still, it's not that good, but you can play around with the parameters, or you can even modify the code using AI. Yeah, so these were the objectives of this particular project, and I was pretty happy with this because I was able to learn something new. And I observed, like, if you change the threshold value, you'll be able to see some more features in your with your edge detection, and that was one of the things that uh, I learned from here. Yeah, so this brings me to end of this video. Thank you all for watching, and have a good day.